Welcome to the 47th lecture of surface engineering. In the last couple of lectures, we have discussed about physical vapor deposition and a special type of PVD, namely the sputtering. In both the cases, we actually did produce, both the methods are essentially meant for producing thin films, typically few micrometers, at the most maybe few tens of micrometers. The essential commonality between both the techniques was that the composition of the coating or the film that we develop essentially will be the same as that of the target. So either we take the material into vapor state by thermal evaporation. Normally this is the basis of all PVD techniques, or else we can use certain ions as projectiles to eject atoms, neutral atoms from the target surface and deposit on a colder substrate, and that's what we do for sputtering. Now, compared to PVD and sputtering, we are now going to discuss chemical vapor deposition, CVD, which essentially is about the same technique. We are thinking about low thickness deposits, films, typically few tens of micrometers or less than that. In the limit, we can create very thin layers, few tens of nanometers in alternate sequence. But the difference is here we actually take recourse to some kind of a chemical reaction. So the film that we deposit actually has a different composition than the precursors. And we don't do any thermal evaporation. We do bubble gases, and we do use heating, both heating of the precursor and as well as heating of the substrate. But most important thing is certain reactions take place in the vapor phase which gets deposited. So if you look at the overall scheme of the deposition process, so you have a chamber, you have essentially a chamber which is so this is the chamber that we have, and this chamber is an enclosed chamber. We have certain heating devices, so these are the heating devices here, and so we can maintain isothermal temperature over a certain temperature zone. Then we have holders, which are essentially stainless steel or some kind of ferrous-based retorts. Now we feed in carrier gas like this. And we actually, when we feed in carrier gas, the carrier gas doesn't react, acts more like a carrier agency. And then we also send certain precursor gas, which at the reaction chamber, within the reaction chamber and the temperature, dissociates and deposits onto the surface. Now, after the reaction, we produce certain byproducts. In some cases, these byproducts are actually fairly toxic, can be fairly toxic, not always, but whatever it is, these byproduct gases actually come out, and they are treated in an exhaust chamber by certain reactions. For example, in this particular case, when we are using titanium tetrachloride as a precursor gas, and we use some other carrier gas, so they mix, for example, hydrogen. So they mix together, and then in the reaction chamber at the temperature, they dissociate. So hydrogen reacts with TiCl4 and produces hydrochloric acid vapor, and that vapor goes into this chamber, scrubber chamber, which is showered with water, and then the acid is collected and then taken out or done the requisite treatment before disposal. So the essential components are the furnace, the enclosed chamber, the retort, the stages on which the samples are mounted. In fact, it can be it's a batch process, and you actually can feed in various sizes, various dimensions of specimens. The deposit composition is fixed, but the substrates can be varied, maybe steel, maybe ceramic, maybe certain other non-ferrous metals. Essentially this is a thermochemical process. So we take the advantage of both temperature and chemical reaction, and is ideal for manufacturing processes like cutting tools, but is also equally applicable to various semiconductor devices. One can produce both thicker and thinner coatings and films. What is very important in case of CVD compared to PVD is that the coating that we develop, the film that we develop, actually is fairly adherent. That's because certain chemical reaction takes place, and when the deposit or the film forms onto the substrate, a certain amount of interdiffusion because of the high temperature takes place, and there could be also a thin reaction layer, as a result of which the wettability is better, or the adherence is better than the PVD or sputtering situations where the interface is always very sharp. Now, so we actually intend to produce a non-volatile thin solid film. So the deposit that it can be, for example, it can be pure metal, it can be a compound, it can be an alloy, but this film that we develop should be essentially a non-volatile one, so that at the reaction chamber it doesn't go back into the vapor state again. And this film is produced by the reaction, and the reaction through certain ionic species is that we create into the vapor phase. The reactant gases, like we saw in the last example, the titanium tetrachloride, they decompose and liberate certain species, atomic species, which react with carrier gases. And what is important is the atomic species in neutral state deposit onto the substrate. Now, it can be atomic species, it can be even a compound, it can be a mixture or a composite even. We'll learn that in course of the lecture. So, the reaction that happens onto the substrate surface is very important, because this reaction makes the coating adherent, and also this is where actually, so the substrate actually in this case acts as kind of a catalyst where the actual chemical reaction takes place. So, this is a fairly versatile process, because you can produce various kinds of coatings or films. You can make powders, I mean freestanding powders, fibers, the growth of very large aspect ratio fibers, or even self-standing monolithic parts can be produced. So compositionally, apart from elemental coating like carbon, silicon, or titanium in some other cases, maybe chromium, these are possible to be deposited, but also compounds like various carbides, nitrides, borides, oxides, even intermetallic phases like aluminides and silicides and so on. So this is widely used in semiconductor industry. I already mentioned the possibilities of making tools on metallic or ceramic inserts. We can deposit in the polycrystalline form, in amorphous form, as epitaxial layer, for example, epitaxial silicon or silicon dioxide layer on semiconductor wafers, silicon germanium wafers, pure metal like tungsten from, say, tungsten WO3, one can actually produce a pure tungsten layer onto the surface, silicon nitride, silicon oxynitride, so a complex compound, similarly titanium nitride, TIN, and even various high dielectric materials. So one can make a conducting coating, an insulating coating, create a dielectric coating, and cover the entire surface or certain areas of the surface. One can also produce synthetic diamond to make extra hard layer onto the surface, even diamond-like coating, or cubic boron nitride, or various kinds of other ultra hard coatings on tool inserts or on components which actually are supposed to experience very high wear and tear. So the process basically follows certain steps. Let's say a typical process like this will have initially you have to feed in the precursor gases through forced convection. So this is how the precursor gases come to the reaction chamber. Then they undergo certain amount of diffusion onto the wafer or the substrate surface, and then they get absorbed. So this is where the reaction takes place, and the desired species actually they get absorbed onto the surface. Then the surface processes begin, which involves decomposition, surface migration, and site incorporation. That means the surfaces are known to have high density of defects, typically point defects like vacancies. So if you have more density of vacancies, free volume onto the surface, then those are the regions where individual atoms can easily come and incorporate. So if I have, for example, certain surface atoms like this, and I also have a vacancy, so an individual atom coming here will find it easier to get incorporated onto the surface. So that's site incorporation. In fact, we also see site saturation through this process. So these 3 and 4 occur together, and then some desorption takes place, which is basically desorption of the byproducts. Like in case of titanium tetrachloride, we found that HCl forms and HCl molecules, they get desorbed, they eject out of the surface, and they are transported as byproducts, and then these byproducts are taken away through the pumping mechanism to a scrubber chamber. Then we shower, we collect the poisonous gases or other byproducts, and then dispose of through the usual mechanism. So this is the overall process. So as you can see, this is a batch process. The substrate, which in this case is a wafer, silicon wafer, but can be any other semiconducting compounds or a metallic component, maybe a gear component, maybe some parts which actually undergo mechanical forces, experience mechanical forces or relative motion, or can be a tool insert and so on. In fact, always remember that the coating that we develop here, since it's very thin, there are 2 things very important. One is that the surface topography has to be fairly smooth, not rough. And number 2, the adherence with the substrate should be very strong, so that we don't lose the coating that we develop. And because the composition wise this coating is different than the substrate, fairly different, then the interface is supposed to be fairly sharp, and that can lead to decohesion. So we need good surface integration. So the heating is, as it is a chamber, is a heated chamber, even the substrate can also have an auxiliary heating system. Now, so we are depositing thin films on metallic or non-metallic semiconducting or carbides or various kinds of ceramic substrates, even polymeric substrates, fairly flexible, and soft substrates also can be given this kind of a CVD coating. So as we saw that we introduce gases into the chamber, that's where the reaction takes place. The energy we supply through heat, through isothermal temperature condition that we maintain. We actually can also apply high voltage in certain cases where we want certain creation of plasma or some other conditions that we want to create. So we can use a radio frequency coupled high voltage supply. So all these are essentially meant for decomposition of the gas that we feed in. And it's not just decomposition alone. Once it decomposes, then it reacts either with the carrier gas or with the substrate surface. And this reaction produces the thin film that we intend. So typically the temperature can be several hundred degrees, I mean easily above 500 degrees centigrade, and maybe up to about 1000 degrees centigrade. In special cases, maybe even 1000, 1200 degrees centigrade. So this process is, this is where it is different than the PVD. Normally in case of PVD, you wouldn't go anything more than 400, 450 degrees centigrade. That's typically to take the material of high vapor pressure into the vapor state. So like I was saying, that you actually can produce a compound layer, and you can feed in different kinds of gaseous mixtures like an hydrocarbon and hydrogen together, or even you can bubble titanium tetrachloride and hydrogen together. So actually The substrate remains inside the chamber. The temperature and pressure conditions can be varied. What else can be varied, and that's what makes this whole process very versatile, is the gas mixture that you feed in. So you can actually close the valve, and then say for example you can close any of these valves or control any of these valves, and then actually control the flow rate. You can even close altogether one particular gas for a particular period of time, and hence during that period you produce one film which compositionally would be different than another film when you are feeding in different kind of gases. So the reactions can be varied, and hence the composition of the films can be changed. Also, the pressure plays a very important role. So pressure wise, we actually can have an atmospheric plasma, we can have low pressure, just a few millibars, or we can have plasma enhanced. We can create a plasma by applying electrical potential difference, and so we can take the help of the plasma to enhance the growth and the adherence of the CVD film. We can even create a fairly high density plasma where we actually intend to produce not only thicker but also more complex films. So all these variations are possible. So the variables wise, we certainly are talking about the temperature, the composition, the pressure, and of course the time. So all these are major important parameters for the CVD process. In case of plasma enhanced CVD, what we actually need is to use two different electrodes and then create a potential difference electrical discharge for electrical discharge, and then you create this plasma. So there'll be a certain amount of dead zone here, and these are the substrates on which you want to deposit. So once you create the plasma, then the deposition is controlled by the thickness of this plasma layer, or the so-called dead sheath that you have in between. So you need the substrates to be grounded, and you need the other electrode actually which will produce the plasma. The capacitive coupling is essential, is the reason why the gases inside dissociate into the plasma state, and the chemical reaction that follows actually now can take place at a relatively lower temperature. So compared to the previous cases where we didn't have the presence of plasma, we saw that the CVD is typically held at about 500 degrees centigrade or above. But because of the presence of these plasma, the same reaction can now happen at a much lower temperature compared to this is the normal CVD temperature range. So this lower deposition temperature is actually very helpful if you're dealing with sensitive materials like a semiconductor device. So there'll be very little damage, thermal damage to the substrate, and yet you can deposit the kind of film that you want, like a high dielectric or maybe a conducting film, whatever you want. So there are certainly distinct advantages that we can see in case of plasma enhanced CVD. So we can restrict the temperature, so we can conduct the deposition at a lower temperature. We can adopt fairly high deposition rate. The film quality is known to be better and actually more adherent. And overall, the deposit that you form is much better or more conformal to the substrate, meaning dimension wise, the contour wise, whatever you deposit will exactly mimic. So if you have a flat surface, there's no problem. But if you have a rough surface, then also the deposit that you form will be fairly conformal to the substrate. Actually, the presence of plasma also helps to remove certain barrier layer, if at all it is present, in the form of some thin oxide or some other reaction products. But there are certain disadvantages. For example, there is possibility of producing certain byproducts, and which may get deposited along with the film. The plasma produces certain chemical reaction. You actually would like to deposit only the desired product, but there could be certain byproducts due to the reaction taking place inside the chamber which may get incorporated. Maybe some complex interstitial compounds or intermetallic compounds may get deposited. But otherwise, kinetically, this is much faster process. Now, in low pressure CVD, which is where you actually are using fairly low pressure, just a few torrs compared to atmospheric pressure. So you have fairly low pressure, and because of this low pressure, generally the growth velocity is much higher at high temperature region. Now, typically in case of an atmospheric plasma, this would be the kind of growth rate. So if you plot growth velocity as a function of reciprocal of temperature, so this is the high temperature region, and this is the region where you see that the normal atmospheric CVD would give you a velocity profile which will be high but will not be very high, but then it drops as the temperature decreases. In case of low pressure plasma, the reactivity is higher, the transport rate is higher. As a result, the velocity also will be higher. So you have a fair amount of higher velocity at high temperature region. So this region, this provision is important because this is where the reaction is mass transfer controlled. So we certainly have these advantages. We have faster growth, we have less auto-doping, meaning ejected atoms from the substrate or the chemical reaction getting doped or reaching the vapor phase and getting doped. So this hazard is less in case of low pressure CVD. The dilutant gas or the carrier gas requirement is low because already we are doing at very low pressure. So scattering or resistance from within the atmosphere within the chamber is less. The gas consumption is relatively low, and the byproducts also are low. Just because the gas pressure is low, so obviously the reactant concentration is low. So so overall, the velocity will depend upon the various partition coefficient and the convection coefficient, and convection coefficient in turn is dependent upon the layer thickness and the diffusion coefficient of the gas, and diffusion coefficient in turn is dependent upon the pressure that we have in the. So if you decrease the total pressure, then you increase the diffusivity, you increase the convection coefficient and also the velocity. So this is how the process, when you make it low pressure, then making it low pressure helps in increasing all these major kinetic parameters, and as a result of which the growth velocity in general is higher at high temperature region. On the other hand, this process, like any other CVD process, is a line of sight process. The step coverage is low because the velocity or the pressure, the availability of the diffusant or the reactant is low, and there is a certain amount of shadowing effect which cannot be avoided. So for very small features, very sharp features, there will be certain difficulty. In fact, this for when the substrate, say for example, this is the stage on which we have these samples. These are the substrates, and now the flux of arrival of the deposits or the molecules or the atoms of the deposit, they'll be dependent upon the concentration gradient, what we have in the gaseous phase and at the surface, and of course the coefficient of convection. Now this actually at the surface, the flux that is available in terms of the molecules per unit area per unit time will depend on the partition coefficient. So what is the level of partitioning happening at the surface? Now, so the overall flux will be when the situation is controlled very optimally, then the flux actually will be equal both in the away from the substrate surface and very close to the surface or onto the surface, because by then one of the steps, which could be due to partition coefficient or the convection or the concentration, will actually make this condition valid, that the flux will be equal both for away from the boundary layer or at the top of the boundary layer or at the surface. So this is what we want. And then finally, the profile, normally the concentration profile varies like this: the concentration profile of the reactant species which we want to be deposited. So away from the surface the concentration will be higher, but at the surface the concentration will be lower, and this is dictated by this both by the partition coefficient and the coefficient of convection. So this is how the Cg decreases over a distance. Now the diffusion, the epitaxial layer that we form, basically the thickness of the species, the concentration of the species, always decreases with distance, like this way. So this is how this is the surface, and this is into the depth, and this is where the diffusion is the maximum active. But then and that's why the concentration is the highest, but the concentration decreases, and then below a certain level you'll reach a saturation. The important point is that this high concentration depth from the surface, this region from the surface, so this is the region which is very important, and control of this can be or thickness of this region can be controlled through the through controlling the concentration terms, and which in turn will be from the feed rate and of course the temperature and other parameters. So this is the example of certain coatings that we can develop. Maybe first you have a PVD coating, and then first you can have a CVD coating, and then you can have a final PVD coating. So this is the kind of a composite coating that you can develop. But what is important is that in case of, like I was saying, in case of CVD, one can actually grade the coating from the depth to the surface, or from the surface to the depth. The coating can be graded, and this is entirely dependent upon what kind of gas you feed in, what is their flow rate, concentration, and other things. One can actually change alternatively the feed gases and make multi-layer coatings, and can make layered structures. And these kind of layered structures is very important, because if you make a very thick coating of a particular very high modulus material, then there is a possibility of greater chance of possibility of spallation or decohesion, because at the interface the mismatch is very large. But if the same coating, maybe a carbonitride or a mixed nitride or a silicide, if you do it in alternate thin layers, very thin alternate layers, then the mismatch is actually accommodated nicely, and the stress generated at the interfaces is minimized, and as a result you actually can make a much more adherent, durable, and mechanically stronger coating on top of the substrate. So what did we discuss so far? We have talked about the mechanism, the definition, the mechanism and scope of CVD, and we realized that CVD distinguishes itself from other kinds of thin film coating techniques by the fact that we are able to deposit a composition which is different than the precursor gases or the vapor that we feed in. And in fact, this is how it actually differs from almost all other kinds of coatings, either from vapor state or liquid state or solid state, because the compositional variation is possible here because of the chemical reaction that takes place. So it's obviously much more versatile than all other vapor-based techniques. The process parameters we have discussed are mostly the composition, the flow rate, the temperature, the time, substrate condition, and so on. The gas pressure is very important, because we saw that in case of low pressure CVD, we actually can increase the kinetics of the process much faster. and also the demerits like auto doping and so on can be avoided to a large extent. The adherence in CVD is better because of the possibilities of not only diffusion but even thin chemical reaction layer at the surface, which makes it more adherent. There are demerits. One of them is, of course, the emission of the poisonous gases as byproducts, which need to be handled carefully. Also, the entire chamber has to be hermetically sealed during the processing, because you are dealing with reactive gases like hydrogen or certain hydrocarbons, or even halide containing gases and so on. So leakage must be prevented by all means. And so we actually also have to worry not only about the chamber but also the pumping devices that we use either to feed in or to extract. All kinds of cutting tool inserts, semiconductor devices, ceramic components, all moving parts which require a very thin, hard, high elastic modulus substrates are ideal for such ideal for such coatings by chemical vapor deposition. Thank you very much.